Physicists have, for quite some time, been interested in dark openings, a peculiarity that has captivated researchers for over 100 years. These enormous entities, which challenge our comprehension of gravity, remain generally undetectable to us. A dark opening with a mass that could be 2 to 4 million times that of the Sun is amazingly powerful. However, due to the research conducted over the past couple of decades, we've progressed from knowing practically nothing about them to uncovering more and more, sometimes in astounding ways. Just recently, a breakthrough has occurred. Specialists, including those at the Kaku establishment, revealed that they've managed to look inside a dark opening. This new information has illuminated aspects of the universe that science might have overlooked in the past. Let's delve into dark openings and discover what lies inside. Space is vast and inspiring. Yet before diving into recent findings, it's crucial to grasp the basics of what dark openings are. Many people are familiar with the concept of dark openings, yet there are still significant gaps in our understanding of them. The idea of a dark opening became theoretically possible in 1916 when Albert Einstein published his general theory of relativity, which predicted the existence of such objects. However, the concept of dark openings remained purely speculative until the 1960s when researchers first observed compelling evidence supporting their existence. While studying the binary star system Cygnus X1, astronomers detected an unusually bright blue star emitting X-rays. This star was not a typical celestial body. It was orbiting around a mysterious, massive object. After further examination, it became evident that the X-rays were not merely floating in space, but were being pulled toward a dense, invisible substance, confirming the presence of dark openings. This was a groundbreaking discovery, proving that dark openings were not just theoretical constructs but real phenomena. The significance of this finding cannot be overstated. It meant that an entirely new class of objects existed in space, requiring urgent and thorough study. Specialists from around the world turned their focus to dark openings with renewed interest. The first recognized dark opening, Cygnus X1, is located about 6,000 light-years away from Earth in the Cygnus constellation. It is significantly brighter than our Sun and has a colossal gravitational pull, so strong that not even light can escape it. This is why it is called a dark opening. The concept of a dark opening is both fascinating and intimidating. It refers to a region in space where the gravitational force is so intense that nothing, not even light, can escape its pull. Anything that ventures too close to a dark opening is inevitably drawn in, destined to be lost forever. This danger makes the study of dark openings not just captivating, but also essential. However, are we in any imminent danger from them? Despite the closest dark opening being about 500 light-years away, this distance still raises questions about potential threats. However, the true nature of dark openings is still emerging. After the discovery of Cygnus X1, astronomers began searching for other dark openings. It is now believed that there may be up to 100 million dark openings in our Milky Way galaxy alone. However, detecting them remains a significant challenge. Estimates suggest that thousands of them exist within our galaxy, highlighting the importance of studying these mysterious objects. The primary concern with dark openings is their immense gravitational force. This pull is so strong that it draws in everything, even light, into itself. The core of the dark opening, known as the singularity, is where all the matter that falls into it is compressed into an infinitely dense point. In simpler terms, dark openings act as massive vacuum cleaners, sucking in everything in their vicinity. If someone were to fall into a dark opening, they would be gradually stretched and compressed until they were reduced to a singularity. This process is incredibly slow, meaning the individual would meet their end well before reaching the final irreversible stage. Yet, despite the apparent danger, dark openings are so widespread that they cannot be ignored. Even though the nearest one is far away, the sheer number of them within our galaxy makes them a crucial subject of scientific investigation. In 2019, researchers achieved a historic milestone by capturing the very first clear image of a dark opening. The supermassive dark opening at the center of the M87 galaxy. This photo was obtained over several nights, with each exposure providing new insights. The data was then meticulously pieced together to reveal a clearer image. The most striking discovery was that a dark opening is not merely a single void in space. It consists of three distinct layers. 1. The event horizon. This marks the point beyond which nothing can return. Once an object crosses this boundary, it is inevitably drawn toward the dark opening. 2. The photon sphere. Here, light is trapped in orbit. Any light entering this region becomes caught in the dark opening's gravitational grip and cannot escape. 3. The singularity. This is the core, where matter is compressed into a single point in spacetime, creating an environment where the known laws of physics break down. This collapse of physical laws is one of the many reasons why studying dark openings is so challenging and intriguing. What's even more fascinating is that each dark opening behaves differently. While they tend to share a similar fundamental structure, the way each one operates can vary. Unlike other celestial objects, dark openings do not emit light, making them incredibly difficult to observe directly. Instead, scientists rely on indirect methods, such as studying how nearby stars and gas behave in their presence. The gravitational pull of a dark opening can cause nearby matter to accelerate and heat up, producing detectable X-rays. This is how many dark openings have been identified. A significant breakthrough in our understanding of dark openings came with the development of the Event Horizon Telescope, EHT, a global network of radio telescopes designed to capture high-resolution images of these enigmatic objects. The first successful image, released in 2019, showed a bright ring of gas surrounding the black void at the center of the M87 galaxy, confirming many theoretical predictions about dark openings. The role of dark openings in the universe. Dark openings play a crucial role in shaping galaxies and cosmic structures. Supermassive dark openings, like the one at the center of the Milky Way, Sagittarius A*, influence the motion of stars and even regulate star formation. Some dark openings power quasars, the most energetic objects in the universe, by consuming vast amounts of matter and ejecting powerful jets of radiation. Despite their destructive nature, dark openings also contribute to the balance of cosmic forces. Their presence helps shape galaxies over billions of years, and their gravitational influence affects how celestial bodies evolve. Could dark openings be portals or gateways? One of the most intriguing aspects of dark openings is the speculation that they could be more than just gravitational traps. Some theories suggest that dark openings might be wormholes, hypothetical tunnels connecting distant parts of the universe, or even different dimensions. While this idea remains speculative, it has fueled numerous discussions in both scientific and science fiction communities. Einstein's general theory of relativity allows for the possibility of wormholes, but no direct evidence has been found to confirm their existence. If dark openings were to function as gateways, they could provide a means of traveling vast cosmic distances instantaneously, a concept that has fascinated physicists for decades. Future research and the search for answers. As technology advances, scientists are developing new ways to study dark openings in greater detail. Upcoming space telescopes, such as the James Webb Space Telescope, JWST, and next-generation radio observatories, will provide more insights into these cosmic giants. Researchers are also investigating Hawking radiation, a theoretical form of radiation proposed by physicist Stephen Hawking, which suggests that dark openings could slowly evaporate over time. By continuing to explore dark openings, we may unlock fundamental secrets about the universe, gravity, and the nature of space-time itself. These cosmic mysteries remain one of the most compelling frontiers in modern astrophysics, promising discoveries that could reshape our understanding of reality. Objects in the universe that we would be able to concentrate on straightforwardly, such as dark openings, must be analyzed by implication. Specialists use perceptions of the radiation produced by dark openings and the gas and residue encompassing them. It's difficult to send a test into a dark opening because anything that crosses the occasion skyline is maneuvered into the peculiarity, where it would be squashed to an imperceptibly small point. This presents a critical restriction for researchers. Without the capacity to concentrate on dark openings in the customary way, scientists are constrained to work with two-layered models to comprehend these three-layered protests. Besides, dark openings come in various shapes and sizes, making it even more challenging to concentrate on them. Researchers have fostered a few hypotheses to explain how they form, with one of the most prominent being the idea that dark openings originate from falling stars. When a star runs out of fuel, it can no longer generate the energy needed to counteract the force of gravity, causing it to collapse. If the star is massive enough, this collapse continues until the star turns into a peculiarity. NASA specialists have zeroed in on an especially powerful world, M87, where they observed a tremendous whirlpool of hydrogen gas rotating at an astonishing velocity of 1.2 million miles per hour. Despite the massive forces at play, the gas did not fly apart, leading researchers to conclude that there must be a huge object at the center of the universe maintaining stability. This object turned out to be a dark opening weighing billions of times the mass of the Sun. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to provide a model for rotating dark openings. Kerr's hypothesis proposed that instead of collapsing into a single point, a rotating dark opening could form a ring of fire or an accretion disk. This disk would rotate so rapidly that outward forces would counteract gravitational collapse. Kerr's work also introduced the concept of the Einstein-Rosen bridge, or wormhole, a speculative passage connecting two distant points in space-time, possibly even linking parallel universes. The idea of wormholes has intrigued researchers for decades. If dark openings are indeed connected to wormholes, they could offer a shortcut through space-time, allowing travel between distant regions of the universe or even between different times. However, even if wormholes do exist, it is unlikely that we would be able to travel through them anytime soon. According to Einstein's theory of special relativity, the speed of light is the ultimate limit for how fast anything can travel, presenting a significant barrier to using wormholes for faster-than-light travel. Nonetheless, wormholes remain a captivating subject of theoretical research. If they were stabilized, they could provide a means of traveling across vast distances of space or even to different times. Some physicists also propose that wormholes could offer a mechanism for time travel. However, the challenges of traversing a wormhole are enormous, as they would likely be unstable and surrounded by extreme radiation and gravitational forces. To truly understand the nature of dark openings, physicists must develop a unified theory that combines both Einstein's theory of general relativity and quantum mechanics. One promising candidate for this theory is superstring theory, which suggests that the fundamental particles of nature are actually tiny vibrating strings. These strings could help explain many of the mysterious phenomena observed in the universe, including the formation of dark openings and wormholes. Superstring theory also proposes that dark openings, wormholes, and other fascinating solutions to Einstein's equations may arise due to the warping of space-time by these minuscule strings. However, despite its promise, superstring theory requires the existence of extra dimensions of space-time that are too small for us to detect. Research into dark openings and their mysteries continues to push the boundaries of our understanding. One of the most groundbreaking ideas related to dark openings is the concept of Hawking radiation, proposed by physicist Stephen Hawking in 1974. This theory suggests that dark openings are not completely dark, but instead emit faint radiation due to quantum effects near their event horizons. This radiation could slowly cause the dark opening to lose mass over time, eventually leading to its disappearance. Hawking radiation is difficult to detect, however, due to its weak nature. Still, this idea provides valuable insight into the behavior of dark openings and their role in the universe. Dark openings also serve as a unique laboratory for studying the interaction between gravity and quantum mechanics. The extreme conditions near a dark opening's peculiarity create an environment where both gravitational forces and quantum effects come into play, making them a key area of study for physicists striving to develop a theory of quantum gravity. The study of dark openings may also hold clues to understanding the origins of the universe. Some theories propose that the conditions near a dark opening could offer insights into the birth of space-time itself. Furthermore, if wormholes do exist, they could provide a mechanism for exploring vast regions of space-time, offering new possibilities for interstellar travel. Although these ideas remain theoretical, they continue to inspire researchers to explore the deepest questions about the nature of our universe.